Okay, if not, then I think we continue. So what I would like to, first of all, suggest to the, I'm going to stay here for a second.
Okay.
So what I'd like to request the panelists is to, first of all, each of you to kindly give 1 or 2 minutes of your view about performance-based design and what you think about this procedure, and then raise some important issue that you feel needs further discussion amongst the engineering community, and especially a response from our speakers. So may I start with Mr. Ellen to kindly just 1 or 2 minutes of what you feel about this method and its applicability.
Thank you. Can you all hear me? Okay. I think I'd like to change your assignment a little bit.
Thank you so much.
Not to just giving my opinion, but maybe asking our guest speaker, because Dr. Ron is here. It's better to use his time here. So one of the, I have many questions, but one of that I already asked you at lunch, but may ask one more time. You know, in the practice, engineers who design tall buildings may have many choices, either to follow prescriptive code-based approach. Maybe they adopt a so-called response spectrum procedure to design the tall buildings against the earthquake, or they can try this performance-based approach. But if one follow the code-based, they may end up with very low shear demand, seismic shear moment compared to the sometimes even lower than wind load. But if then for the same buildings, for the same earthquake, if we try performance-based approach, we may come up with a very high demand compared to the code-based, maybe 3 times higher in shear and somewhat much higher in moment. Now, there's a problem here. Because the code-based is much easier, performance-based require a lot of skill in making a nonlinear models. A lot of engineering hours need to be spent to make this. So people do not want to do performance-based. They do not really need to do that. Okay, and if they follow that, they end up with a much stronger demand. So a lot of problems coming here. Although I am in academic area, we believe that performance-based is better. But in practice, then how do we solve this problem?
Okay, tough question. So I have to admit that I'm not as familiar with the Thai building code as I should be, perhaps. But I know, and I can speak in the context of ASCE 7, which forms the basis of the US code, that in ASCE 7, for example, for a reinforced concrete shear wall building, the height is limited to 80 meters. And if you want to build a building taller than 80 meters, either you cannot use a concrete shear wall, or you must supplement that concrete shear wall with a moment frame dual system. You must, by code prescriptive rules, once you cross 80 meters. Almost all of the buildings that I showed you, not all of them, but most of the buildings I showed you are much taller than 80 meters, but they only have concrete shear walls. And the idea is that in order to demonstrate that the building performs equal or better than the code expectations, while it's outside of these otherwise restricted areas of the code, height restriction or system restriction, this allows us to do that. So you would otherwise not be able to design these buildings as they've been built. So that's the benefit. In Thailand, I don't know if you have the similar height restrictions or systems restrictions. Is it ASCE 7 based, Dr. Emma?
Yes, yes.
So the same restriction exists here in Bangkok then, that above 80 meters, you would be compelled prescriptively to have a reinforced concrete core and a perimeter moment frame, for example, and you must, if you're going to follow the prescriptive requirement. Whereas if you had just the concrete core wall, you're able to design that building using the performance-based approach. And yes, the shear demands are higher, but you've eliminated completely the moment frame.
Yeah, basically, your answer is if it exceeds 80 meters, we have no choice but to go to performance-based.
It's not that you don't have a choice. You can still, but there are limitations on the systems you're able to use that would be considered code compliant.
Okay, but what I see in many countries, what I have heard in Pakistan, in Indonesia, in Philippines, in Thailand, even in Myanmar, they just apply the code base without looking at the limit. Because it is in AC7, and AC7 has been used as a model code in many countries. And when we tell them, okay, this is going to give you, is going to underestimate the real demand, I think nobody really listened to this. Well, I'm glad that you show that performance-based design will give us better understanding about the real demand, allow us to do better design. Anyway, problem may still stay with us.
So I might add that in tall buildings, and when I say tall buildings, I'm going to say very tall buildings, 300 meters, 200, 300, 400 meters tall, that the structural systems that are generally viewed and proven as the most efficient. So for example, either say a core wall building with an outrigger system, or instead of a core wall building with outrigger system, say a perimeter mega bracing system. Neither of those systems is recognized in the prescriptive language of the code. So by virtue of that, you're outside of the code. And I know in many jurisdictions there isn't a rigorous review process by the local authorities. So maybe it's not adhered to. But in the US, where there is a rigorous review process, you'd be viewed in those instances as being non-compliant.
Okay.
And so those systems, core wall with outrigger, or mega bracing, or any kind of other unusual structural system would be viewed as non-prescriptive and outside the code. And so the only way to do that is within a performance-based setting.
Can I just add to that? In fact, sometimes in some buildings where performance-based design wasn't done, but the building was not compliant with the code, and so, I mean, what I mean to say is it's higher than 80 meters, and it has a small frame and a core wall. Then if you follow the code literally, then you need 25% to be allocated. So which means that the frames become excessively heavy because they have to be designed for 25% of the demand, even though the real demand is only 5%, 10% because of the layout. So that I think if you really follow the code, it may become more expensive than if you do a PVD on a project of that kind and let the frame be as it is. So that's what we have found in some projects as well. Just to add a comment on that.
Okay. Well, I have many other questions, but I keep it after the other.
We'll let Billy talk for a while.
Oh boy. Okay. So actually, it's been a long time since I've touched design. So some of these things, just to put things in context, actually, one of the things that Ron brought up that I was going to mention is we always ran into this, especially with outrigger buildings. You know, without performance-based design, what's your R factor for an outrigger building? As you said, it's outside of the code. It's not compliant. You know, there's no way to check that. So of course, performance-based design allows us to get more into what that actual, how effective that outrigger is, and especially again with the dual frame system, as you mentioned. Like once you actually calculate it, you know you're never activating that dual frame. And so we always looked at performance-based design as a means of potentially saving a lot on the structural costs because of that. And before asking you one question, I'll share some context with you. So we had a project in Jakarta that was over 500 meters. And the local review authority, the local, well, not a code authority, but They had an ASCE 7 base code, but the review board said, well, we want you to do performance-based design. I said, okay. So we started engaging the designers to do this, and we said, okay, but when we come back with less forces, we're going to be able to use those, right? They said, no, you still have to use the code minimum. I said, okay, well, that's then a performance-based check of the code. And we pushed and pushed, and the big problem we had was, well, two things. As the design developed, they made us go from ASCE 7 2005 to 2010. So we went from a 1% minimum base year to a codified minimum base year that ended up being closer to 3% in our case. So that's a big jump. That's 3 times base year automatically. And we said, well, look, we're doing all this extra rigorous calculation and for the performance-based design. Why can't we use this? And the big stumbling block we had was the performance criteria acceptance. We could not get the local authorities to accept a performance criteria that was anything other than the code. How have you dealt with that in other places?
So how we dealt with that is through a peer review process. That, depending on the jurisdiction, where we go through the most rigorous reviews are, say, in San Francisco and Los Angeles. And in those jurisdictions, the local authority in San Francisco requires a panel of 3 peer reviewers. One is a practitioner, one is a researcher, a professor, and one is a seismologist. And that panel of 3, their objective is to ensure the design meets the performance objectives of the code, but you're able, through discussion with them, to if you're able to demonstrate your design is appropriate and properly backed up with research or analytical studies, that they can accept that, even if it's outside the code. And so the peer review kind of opens that door, and that process has been very, what's the right word I'm looking for here? Anyway, it's become the norm in many jurisdictions that we work in around the world. And so not just my passionate plea to have you all engage in peer review, but I don't know who your local authorities are here and how much weight they carry, but encouraging them to encourage that process is healthy for everybody. And that maybe opens the door then to allow things outside of the prescriptive code to be implemented. You have to recognize, right, that the code is written by people like me, and we get it wrong all the time. And we're always trying to correct it. And so you just have to know that the code is written by mortal human beings, not by God or Allah, or it's not the Bible. It's the best that we have at the time, and it continues to change. So breaking the rules is okay as long as it's properly got science and engineering behind it.
All right. Thanks a lot for the presentation. It's a great presentation. Now, I'm going to break my question into 2 parts. One is it's based on my experience that I've been using performance-based design instruments, and the other one is the problem that I see, not the problem, but the question of challenges that I might take the input on. So definitely the performance-based design is the way to go, and my experience is with the retrofit of the building in California. Now, that definitely saves costs a lot when you compare it to prescriptive code base. Now, there's one project that we did, which is a new design for the hospital, the military hospital. When we're talking about using performance-based design in new design, what we did was we were using prescriptive first to get the sizes of the structures. And then we put the same structures into performance-based design, and then there's some adjustment to achieve the performance that we need. And now one thing that we found is doing performance-based design is you need to have, what the person is doing, need to have experience in doing it. Like you said, you put in garbage in, you get garbage out. That's one thing. The other one is, it takes a lot of engineering time to get to the point where you have the right structures. So you need to have the leverage between time and see the client will come to you and say, a certain thing, right? They don't give you enough time. That's the experience from the States. Now, I see it's going to be the same thing here in Thailand. How would you, do you have a recommendation on leveraging it to make it work?
Oh, that's a tough question. I know the clients like to go faster and faster and faster. And especially if you're just starting to do your first performance-based design, then you have a very steep learning curve. These two things may not go together very well, so perhaps you're best served by not trying to do your first one on a project where they're trying to go so fast. I know that's not always practical, but that's the reality of it, because you're right, it does take a lot more effort, a lot more rigor in the work. And in particular, when you do your initial sizing, your initial proportioning, if you have a fair amount of experience doing it, you know how to go about the proportioning, but if you don't, you could very easily be surprised later when you do the nonlinear response history verification, and you find out, for example, that the shear demands are 3 times higher than you otherwise expected. And now what? You have to make the reinforcing in the wall twice as thick and twice as much, or 3 times as much. This is a problem. And so I think picking, if you're going to do it for the first time, number one, pick the right project and client to do it with. And number two, get some outside advice. I'm supposed to not advertise here, but Dr. Anwar and I, we're available. Right? Send us an email. We'll gladly share with you our advice. Honestly, my desire is to have people use this methodology and do it properly. And so I'll gladly help anyone answer questions and help you down the way. And if I get paid, fine, and if I don't get paid, I don't really care. It's more that I want you to do it right. And so I'm gladly, help you answer questions and let you go on your way. And that's just not me. I think a lot of us that are in that space want to help each other to make sure we're doing it properly. I'll just add 1 or 2 other comments. So I get a lot of attention for being kind of the instigator of all of this. And the fact is that I stole from someone else. So what I mean by that is ASCE 41 was created long before we did performance-based seismic design. And in the retrofit world, as you mentioned, performance-based methodologies were born in the US in the seismic retrofit of buildings. And what we did is we adopted that methodology and technology to the design of tall buildings, which is what our practice does. So we borrowed from something that already existed and we extended it. Also, it should be noted that in Japan, they've always done performance-based design, always. That's the basis of their engineering practice in Japan. So if you put it in that context, and I'd also say in China. Now China has some weird regulations unto itself, but the fundamental basis of their seismic practice is performance-based design. And so, the US doesn't have any monopoly on performance-based seismic design. There are at least 2 other major cultures and countries in the world that are practicing it. It's slightly differently, but a similar framework. And so we talk about it in the US context, ASCE 7, but it should be noted that the Japanese have long been doing this for 50, 60 years already, and the Chinese as well. So we're just talking about now in kind of the US context.
Okay, thank you. Thank you very much for coming to Thailand. And really impressive presentation, especially for the last section of your presentation that you give the cases. That is exactly hit to my heart, because we have the same problem. And the cases you mentioned, like the soil structure detection, we don't know what is the reality when we design the building. The auricle, yes, but we just consider it as a very stiff auricle, so we go for the worst case. for the soil structure is also for the roof test. And also the ground floor peak moment that is maybe higher than the base in the basement. This is really true. But what I would like to ask is that in your experience, what is have you ever experienced any project that the designer at the beginning, they design by the prescriptive code, and then you review by the performance phase, and then you found that there are some areas in the building that you need to strengthen or to repair or to upgrade in your experience?
Yeah, so I can't think of a building where we've had to retrofit or strengthen, but I'll say this, that when we first started doing performance-based design in the mid-1990s, before we actually implemented it in construction, we did several buildings where we did parallel designs. We did a prescriptive design, and that's in fact what we built. And in parallel, we did a performance-based design to try and learn how to do it and understand what the results look like and discover things like shear amplification. And so before we actually implemented our first performance-based design for construction, we'd already practiced a few times and kind of knew where these problems were. So we avoided, I suppose, that need to be surprised and have to retrofit. That maybe goes back to the earlier comment. There's a way in which you can maybe get up to speed. If you haven't done one before, run parallel designs in your office. Do the prescriptive design and build that. But in parallel, do a performance-based design to just teach yourself. This is how we started 25 years ago or 22 years ago. We did, I think, 3 parallel designs before we actually built a building using that methodology. And we learned a lot doing that. So, anyways, yeah.
Sitting. Your turn again.
May I?
Yes, please.
Maybe I should ask Dr. Kitipat about the Mahanakon project. That I think it was designed maybe by code base and checked by performance base. And there's a problem of shear amplification as well. Can you say something about that?
Put him in the right time.
We didn't do the performance design 100%. We just followed the CTBUH guideline only at the last section of the guideline, which is the Appendix B, which is the elastic analysis for the performance-based criteria, which is still elastic analysis. But we try to follow this guideline, and as Ron said at the beginning, that takes time. So we decided to go for the conservative assumption. So we used the 2,500 years to upscale the code base response spectrum. So it go up by 50%, and then we try to reduce the damping ratio. Instead of 5%, we use 2%. So it's another 25%. And we don't have any R because we just want to see that we have figure under the MCE, the maximum earthquake, considered earthquake. And then we just check the stress in each element, whether compared to the normal strength, how many times that is over the strength. If it's less than 1, then the guideline says that you don't need to do anything because you already upgrade the demand by almost 2-3 times. then if it's still under the normal strength, it's still okay, and then you don't need any ductility detail. But if it's more than one, but not greater than two, then you need the ductility details for those areas. But if it's more than two, then you need to change the section. So I did that. So it's not the non-linear so-called analysis. It's just only the elastic analysis, but just to see how many times it over the strength. And the result is that when I design by the code perspective, I just use I equal to 2 instead of I equal to 4. Because like Klemencic said, you always design the first section by the prescriptive code first, and then I cannot come back to change because it's already cast. So, because it's a design field, so we need to make sure that we will not have any problem after. But that's why I asked this question that after if we follow the prescriptive code and check by the performance test, where in your where is the location that we have gotten, because we will try to avoid that in the future. That is my concern.
So I might share one or two thoughts before they are lost on me. I shared with you a number of these more recently published guidelines and documents. And I want to talk just briefly about a couple of them. First of all, let's talk about ASCE 7. So ASCE 7 has come out recently with a new version, ASCE 716, which most jurisdictions around the world have not yet adopted. In the US, ASCE 710 still is more or less the legal document that guides the code. But in 716, there's a number of changes that are very important. There is a whole new chapter on nonlinear response history analysis included in ASCE 716, which is good because it kind of further legitimizes that approach. But it should be noted that included in that chapter in ASCE 716, the ASCE authors have chosen to tinker with the strength reduction factors, the phi factors for iron reinforced concrete design. ACI is very upset about this. And ACI thinks what ASCE has done is wrong. And so in response, ACI is writing new provisions to correct ASCE 7. So ACI 318.19 will include in it an appendix, which I'm writing right now, that will set the record straight on what the appropriate phi factors are to be used in the nonlinear response history analysis setting. So, if you use ASCE 716, be aware that the phi factors for RC design are in dispute. In most regards, they're incorrect and they're actually too high. Instead of 0.8, they're using 1. Or, for example, just be aware that the phi factors in ASCE 716 are viewed by ACI as wrong and will be corrected. The other item that's in ASCE 716 that's not clear is if you have an element that has axial load and bending moment on it. So a column in a moment frame, for example, where you have axial moment interaction, PM interaction. How is that element to be viewed in the context of a force-controlled element versus a deformation-controlled element? ASCE 7 is not clear on how to approach that. The appendix to ACI 318.19 will be very clear and will help you understand how to go about that. In short, axial demands are going to be viewed as force-controlled demands, force-controlled actions, and flexure is going to be viewed as a deformation-controlled action. So in other words, in a moment frame column, to be very specific, you'll be able to allow some amount of flexural yielding to occur in the column, so long as you don't exceed the axial capacity. And so that's coming. A few other things that I know that are being changed as we speak. I mentioned earlier in the TBI guideline, 2.03, the load combination for force-controlled element assessment has two factors in it which at this moment are viewed as too conservative. One is there's a load factor of 1.2 on dead load. That is acknowledged and viewed as too conservative for that particular assessment. What is the right number? We don't know yet, but I think it's going to be 1.05. Hopefully in a month or two's time we're going to release a new version and you'll know the answer, as will I. It will be something less than 1.2. The other part of that equation that's in great debate right now is vertical ground motion amplification. So there's a term which is 0.2 SMS that's in that equation. And for example, I'll just share this example with you. We recently took a building that we've already built and designed to the old TBI guidelines, TBI 1.0, and we took that design and we ran it through TBI 2.03 to see how the design would otherwise be impacted. And what we discovered in that building was that the columns supporting gravity load, not even those columns that are part of any seismic bracing system, the columns supporting gravity load, when viewed through the lens of the new equation in 2.03, would need to be 50% larger. 50% larger. That's the problem. And you wouldn't know that result until at the end of your nonlinear response history analysis. Now think about that. You're nearly to the end of your design trying to verify your design, and now you need to go back to your client and your architect and report that my columns all need to be 50% larger. Congratulations, you've just been fired. So we know this is a problem. We're trying to fix it. We don't know what the fix is yet. Like I said, there's a group at UCLA and a group at UC Berkeley working on it as we speak. Hopefully that will be corrected shortly, but the vertical ground motion impact is in question right now. Of note also, you saw there's this other document that's published by the Los Angeles Tall Building Structural Design Council. In structural engineering circles on the west coast of the US, there's a long-standing competition between Southern California and Northern California. And they tend to try to outdo each other. Well, in this particular instance, as it relates to vertical acceleration, apparently in Southern California it doesn't exist, because in the LA Tall Buildings recommendations, there is no factor for vertical ground motion acceleration, whereas in TBI, which is largely written by guys from Northern California, there is. So there's the dispute over the view of that, and so if you, this is a little facetious, I suppose, but if you get stuck and you find that this vertical ground motion is giving you a headache, throw the TBI in the garbage and use the LA document, because it doesn't have that load combination. I'm being a little facetious, but just know that this is evolving, right? And so don't be so beholden to just reading the words on the paper. Try and understand what's behind them. And if you get stuck, or if you have a question, send me an email or send Dr. Anwar an email and we'll try and help you sort it out. There's a lot more too. I can't even remember them all, but those are some of the highlights. Or lowlights.
Yeah. One more question?
I still have a quota?
Yes, you have. Maybe the last one.
Unlimited.
I thought I used up all my quota already.
Unlimited quota.
Well, I'm very interested in the vertical ground motion effect, but I may ask you later. But let's focus on this one. About the ground motion, but maybe most of the audience are structural engineers. The ground motion that we use, normally we follow some kind of a code-based spectrum. And the code in many countries, the design spectrum are very similar, and similar to the spectrum shown in AC7 in the US. It looks almost the same. And if it will be adjusted by the local site condition, will be only a small factor based on a shallow soil condition, VS30 and something. But what the ground motion we saw in many sites in Mexico City are long period ground motion in deep basin. In Kathmandu, extremely long period. In Taipei also, about 1 or 2 second predominant period. In Osaka Bay, very long period. So I think in many large cities located on deep soil basin, we are going to experience a ground motion that looks very much different from the spectrum assigned for those locations. But to understand the right ground motion, maybe it's difficult. Even I think your project in Philippines, in Manila, there's people study the basin in Manila, but they do not count that yet come up with the design spectrum. So how do you handle this problem?
This is a very good question, and you highlight a great need of our industry, of our profession, that we need a lot more work done in the area of site-specific assessment and seismology. There's so much work to be done around the world. Part of it is difficult, right, because the data doesn't exist. And so oftentimes you're trying to extrapolate from Mexico City or from Osaka or some similar geographic or similar geology type conditions, and you're trying to extrapolate to a local condition. And it's thoughtful work, but it's hard work. And so we need a lot more of that. In fact, one of the areas maybe that is the most, we're the least confident, is in the area of ground motion. And that's why I say on the west coast of the US, where we have lots of data and lots of experience and lots of very knowledgeable people, our confidence is higher. And when we're working in other locations where the confidence isn't as high, we have a project recently in Jakarta, and we know the ground motion definitions there are suspect. And so we're proceeding more cautiously with the design than we might otherwise. We're not driving it to the very kind of fine point of the pencil, right? We try to make it a little bit more conservative in a way, recognizing that input ground motion is a little less known. In time, hopefully this will become an area of great study. Researchers like yourself can help us advance this and define more thoughtfully and clearly what is the driving ground motions in Bangkok, for instance. So when we design the next Mahanakan Tower, what kind of ground motion should we in fact be using? Definitely probably long period motion. And what does that spectra really look like? What is the shape? So lots of work. So I think you should feel like you have many, many, many more years of work ahead of you.
Fighting back.
Okay, thank you so much. We will probably continue a little bit, but I would like to encourage some questions from our participants, our students, and also our participants. Please feel free to ask some questions. As you can see, it's a good opportunity. Not only we have Ron, who is our keynote speaker, we also have other experts and other colleagues here who might also be able to shed some light on some of your questions. So, any questions, please feel free. Yes, please.
Good afternoon, gentlemen. I am very proud to be from the Philippines, and my office is started from the engineering consultancy, and our business is in line with analysis and retrofitting, as well as seismic instrumentation of buildings. Now we are talking about 11 kind of response spectrum for the upper limit and the long period. Now what if the acceleral rocks reads more than that? What happened to our PED analysis? Sir?
I'm not sure exactly I understood. If you use less than 11, you're saying?
No, I mean, what if the response spectrum plotted based on the acceleral rock reading now exceeds that? So what happened to our PED analysis now?
I think, if I may, like, this is related to what we discussed in the morning because they're talking about instrumentation and the accelerogram they have installed in the building. So we are getting the readings from them. So if I, please correct me if I'm wrong, the question is that if we get a reading, because we are getting the acceleration plots from down and mid and top, and can we use that information, first of all, to generate the response spectra that we can use to check the building? And or is that information useful to reconfirm DVD again with using actual information from the ground motions record? Is that the question?
Yes, sir. Yes, sir.
Yeah, okay, thank you for clarifying. Yeah, that's really useful information. We've been trying now for my entire career in the US to get our clients to allow us to monitor their buildings. And so far, I have one. And mostly it's because the clients are worried that if there's this data out there about their building, that somehow the competition will get a hold of that and somehow make their building seem bad. And so the clients, at least in the US, have been very reluctant to allow us to monitor their buildings. So forgetting those problems from a purely engineering and scientific point of view is totally useful. It'd be, in fact, we were at one point trying to sell that as a service in the US, as a rapid response post-earthquake, that if we had a monitoring system in the building pre-earthquake and knew the signature of the building pre-earthquake, and then the earthquake happened, and then we can look at the signature of the building post-earthquake, we can very rapidly assess if there's major damage or not major damage, without even going to look at the building. We just look at the data. And they're call it building health monitoring. I think it would be wonderful if we had all of our buildings monitored this way, so that we as engineers could learn and make our designs better. But then also in an earthquake response mode, we're able to much more rapidly assess where there's damage and where there's not. Unfortunately, where I practice mostly, don't have many clients wanting to take that. If you're doing that well in the Philippines, congratulations. I want to get some of your data.
Can I just add on to what Ron is talking about? Back a few years ago, about 2 years ago, in California, one hospital, new hospital, was to be instrumented by law. This hospital was the local jurisdiction for monitoring of the hospital. They require that the owner of the hospital has to use instrumentation. And the good thing from an engineering standpoint is they're trying to use those data to calibrate with, say you have a hospital with all this instrumentation and the engineering model, and try to match the ground acceleration with the floor acceleration. If you have that model in place, when the earthquake hits, then they can actually know the damage of the buildings, and they can go without having to go to the hospital.
Actually, as I mentioned in the morning, we are also trying to work in the same concept, and we are trying to convince some of the people to give us the data with signing an NDA and all, so that it would be just, But I think this is a goal line. I keep telling people that if we can get that data and everybody can learn from it, it will be just useful for everyone. In fact, involved in this, all the stakeholders will benefit if we are able to get the data and, like you said, get the pre-earthquake model sort of calibrated, then it is okay.
So on that specific subject, the one Rincon Hill Tower in San Francisco, the poster child for seismic engineer performance-based design, that building is the one building that we have monitored. It has 72 accelerometers in it, so it's very extensively monitored. And during the last 2 earthquakes, we've written technical papers on the results that were of the recordings. So there are 2 published papers with the results of the most recent one was the Napa earthquake, which occurred, I think, 2 years ago. And during the Napa earthquake, we recorded the building motion in that building from all the sensors, and there's a paper published on that. So you might find it interesting just as a reference for your own work to see what we're doing there, because that building is very, very extensively monitored.
Thank you. Any other questions from the audience? I think this is a good one. Yes, please. you have it now? Okay, just, yeah, this one and then. Can we get the mic?
Okay, good afternoon, Ron. Thank you for your presentation. You mentioned about the global activity factor R is ranging from 2.2 to around 8. And I still remember maybe 20 years ago in ASCE, they even have used 12. Right? Now, my question is, how will the PVD analysis affect or R affect with the PVD analysis, where in your presentation I've seen that the strain in concrete didn't even reach 0.003, meaning it's around 0.001 by. So therefore, it doesn't even have reached the limit, the inelastic limit of the material. And with that, therefore, the material is still somehow within the elastic range, and therefore, it will absorb a lot of stresses. So how would R affect the PVD?
Yeah, so there's a couple of things to note that are maybe a little subtle, so I'll try and shine a light on them, right? So the results I showed you for that building where we're assessing the strain demands in the building, the compressive and tensile strains, what we're doing there is we're modeling the building as accurately as we can, meaning we're not using design material properties, we're using expected material properties. So instead of 8,000 psi concrete that's designed, it's expected at 11,000 psi. So inclusive in that model are things like expected material properties, expected loading conditions, not design loading conditions. And so if you have to separate in your mind, in PVD at the maximum demand levels, we're seeking to verify the design under realistic conditions as best we can predict. Whereas if you go back to the code prescriptive design, you're working in a design environment where you have load factors on dead load factors on live load, design material strengths, et cetera, et cetera. That's where R comes in. And so in that context, you'd find with R that, in fact, the building seems to be yielding. But in fact, in reality, it's not. So I know it's a little confusing, perhaps, but keeping kind of the verification process separate from the design thinking is important. That all said, in most tall buildings that I've worked on, the nonlinear demands in the buildings have been very modest. I'll call it an effective R of in the 2.5 to 3 range is not uncommon. We're just not pushing the buildings very hard, and the reason being, by and large, in those buildings, the resonant ground motion might be 1 second, 1.5 seconds, and the resonant period is 6 or 7 or 8 seconds. So they're not in resonance, and so you never drive the building very hard, and thus it never really yields. The code prescriptive language doesn't capture any of that. And so I often say that most of the tall buildings that are designed in seismic zones today, not only are they very thoughtfully designed using performance-based techniques, but they're naturally protected because of the dynamics of the actual situation. The buildings that are most vulnerable, depending on what city you're in and what location you're in, but I'm going to say the buildings that are in the 10 to 20 story range. Those buildings are prescriptively designed without any consideration of shear amplification, many times not constructed particularly well, and in complete resonance with the ground motion. 1 second, 1.5, 2 seconds. This is why in Mexico City in 1985, we saw so much damage in mid-rise buildings is because the resonant ground motion in Mexico City is 2 seconds. And the buildings that started off at 15 stories, by the time they cracked, their resonant period was 2 seconds, 2.5 seconds, complete resonance with the ground. And so those are the buildings that are going to be, I think, most vulnerable in the earthquake. And that's not just subject to Mexico City, I think that's worldwide. In Manila, for instance, the buildings that I think are in the gravest danger, if you will, are those mid-rise buildings. Not so much 80-story building, but more 10 stories, 12 stories, 15 stories. This is where the concern is.
I think this is the last point is very critical, and in all the post-earthquake pictures that we saw, we hardly see damage to very tall buildings. The low-rise that we see mostly, but there are other reasons also, maybe some other time. So, questions to you.
You mentioned about considering the soil spring interaction in the modeling of the building. Would it suffice to consider the spring interaction at the foundation footings and then maybe at the ground beams and the level of beams along the basement floors up to the ground level? Or is there any other clear-cut considerations that we could make with that?
Yeah, so soil structure interaction I mentioned is it's kind of uncharted territory. We don't have a lot of benchmark data to judge our analysis against. I'm gonna try and simplify the discussion here a little bit. So traditionally we have not considered soil structure interaction. Today we have the tools to allow us to do it, but most of the guidance that we receive from our academic colleagues view the building in what I'm going to call a free field setting. Meaning, yes, there's soil around it, and yes, there's a foundation, but it doesn't acknowledge that the fact is that that building probably resides in a city. And how do all the other surrounding buildings and their basements impact that building? In a textbook, it's viewed as in a free field. There's nothing around it for miles. And so then there's an analytical solution to that, perhaps. But the minute you put it into a very complex setting like a city, where the building to the left has 5 basements, the building to the right has no basements, there's a subway in the street in front of you, and there's a big excavation behind you. How do you analyze that? That's why I say it's very complicated, and our confidence is low that we really understand. If we put springs and dashpots in our model, we can do that, but how close to reality is that really? And we don't really know. So I'm not a big advocate of soil structure interaction right now for most instances. I can understand in a few where it's important. And I'll kind of leave a final comment on this way, that in San Francisco, the tall tower that I showed you, Salesforce Tower, is immediately adjacent to the new transit center. In fact, they touch each other below grade. And the question was, from the government, how does your tall building impact my transit center? And you need to design your tall building so that you do no harm. You can't design a building, and we won't approve a building that in some way negatively impacts our transit center. So in that case, we worked with Arup, who built a very, very elaborate model of our building, which we contributed input to. They built a model of the transit center and all the surrounding soil, and we modeled them together. And to my knowledge, it's kind of the most elaborate soil structure interaction model I've ever seen, that I'm aware of. And the issue there was to demonstrate that our building did not have any adverse effect on its neighbor. So that was one instance where it was deemed by the authorities necessary, so we did. Outside of that, we try to avoid.
Any other questions? Thank you. Let's see.
Hi, good afternoon. Thank you very much, Ron, for the presentation. It's not a question really, it's more I want to ask for advice on practicality, because when you do performance-based design, there's a lot of computational effort going on. For example, you have a building, 4, 2 towers sitting on common coding, and eventually during the construction, it will not be constructed simultaneously. So, how do you deal with this example, only one tower will be constructed, and then another tower, then the third one before the final tower. So in terms of practicality in modeling and analysis, because it involves lots of computational time. How can we do this now in a practical way?
There is no practical way. We have done buildings where there have been as many as 4 buildings on a common podium. Fortunately, in our cases, I suppose they were all built simultaneously, so not phased, not one by one by one by one. If we were faced with the phasing question, at least at the moment, I'd have to think about it more, but we'd be feeling compelled to analyze each and every condition. So it quadruples the amount of work you must do. But the point is that the diaphragm that connects all those buildings together is very critical to the overall system. And to understand the diaphragm demands as these different superstructures drive the dynamics is really important to understand. Or, if you want a practical solution, put a joint in. I mean, facetious, but right? That's a way to solve the analysis problem, is to separate it and not worry about it. But if you can't put the joint in, then I don't know that there's another choice than to kind of rigorously go through the analytics.
Actually, we went through that practice with the park terraces on the project that we did together, and that was built several years in between, and we had to go through several simulations of 1 tower, 2 towers, 3 towers. It's not an easy thing to do. It's really the pain. Okay, Phil, I think we are just about running out of time, so I would like to say thank you so much to the speaker, of course, and to the panelists, and to the audience. After this, what's the plan? We will have a coffee break, as I presume. Photo session, yeah, okay, maybe you can announce that. So I'll give the mic back to the call. So thank you once again, thank you very much. Please bear with us for a minute for the announcements. Thank you.